Topic 2.8 is titled Inverse Functions. Now, you've technically seen these sort of things before in a previous course. It also makes sense to you because if I were to ask you, what is the inverse of addition? You would say subtraction. What is the inverse of multiplication? What is the inverse of squaring? Square rooting. So we understand the concept of inverse functions, inverse relations. They undo each other. We can find these things by switching the x and y value. You're going to hear me say switching the x and y value a lot of times today, but that is so important for what we're doing. We are switching the input and outputs and resolving the equation so the outputs become the inputs and inputs become the outputs. And the reason we have to take a little bit to study inverse relations and inverse functions is because there's no obvious answer like addition, subtraction, multiplication, division, square rooting for me to ask you what's the inverse of exponentials. There's not a clear answer until we go through this idea. So this is how you write the notation for an inverse function. It is called F inverse. Everybody say F inverse. Nice. So if I ask you a question like that, F inverse, I'm asking you to find the inverse or the switching of the x's and y's in the problem. So we get a really green basket that says chargers on it. We have a really big definition for class coming up right here. On a specified domain, a function f has an inverse function or is invertible if, let's highlight with yellow, if each output value of f is mapped from a unique input value. What that is saying is that each output value coming from a unique input value means that your function passes both the VLT, vertical line test, that's from Algebra 1, the vertical line test, yes, and what's called the HLT, called the horizontal line test. That means that you have no repeating x's and no repeating y's. But we can't say it like that. I need us to use the definition of an inverse function, which is right here in the yellow. So we're going to be writing this definition over and over again today. And if you're getting stuck and you're like, where is this coming from? It's the definition of a one-to-one function where each output value is mapped from a unique input value. Additionally, two functions are inverses if and only if f of g of x equal to 1 and g of f of x is equal to x. I think I said 1, but I meant x. If we can compose the functions both directions, we can prove or show that two functions are inverses. The last big piece of information about inverses is that graphically, inverses are reflections of each other over the line y equal to x. So reflections is like when we flipped over the x or flipped over the y. This time we're going to flip over the perfect diagonal with a slope of 1 and a y-intercept of 0. So we're going to be drawing diagonals on our graph and flipping things over. But let's just make sure the basics of understanding what I'm asking for when I ask for an inverse function is clear. So we have this table, and we're going to use the relation shown in the table to answer the questions. The first part says f of 6. Don't overthink it. If this were class last time, how would you answer f of 6? 2. Nice. That's correct. How about f of 3? 2. How about f of 4? 0. Okay, so we get it. That is the input value. We give the output value. But what if I ask you f inverse of 0? 4. Nice. How did you know that's what I was asking for? Yeah, everything's opposite. We're switching the x's and y's. So f inverse of 0 means look at the outputs for 0 and tell me the input. So my question for you guys is now, what is f inverse of negative 1? 1. And I want you to think about this one for a second. What is f inverse of 2? 3 or 6. Nice. Interesting, right? We have two options there. We have two options for what the answer can be for f inverse of 2. Keep that in mind for a question I'm going to ask you later. Part C says the table shows a relation only or a function because this is similar to the question I asked you at the door. Is that table a function?
No.
Why not?
No. Because it has.
Wait. It's the y that can map to the x.
So yes.
So at the door, remember when we came in, I said what couldn't repeat?
X.
The x's. Did any of those x values or input values repeat? No. So this one is a function because all input values are unique. That's the mathematical definition of saying can't repeat your x's. All input values are unique. But the question goes on further, and it asks you, is this table invertible? This is where we have to look at the outputs, because the definition that we highlighted in yellow at the top of our page says a function is invertible if each output is mapped from a unique input value. Did this one output, 2, get mapped from a single x value? It got mapped from 2 of them, right?
Yeah.
So is this invertible? No, this is not an invertible relation or function. It is a function because, and here's the definition, the things I want to have you practice writing down. We would say the table is not invertible because all output values are not mapped from a unique input value. That's the definition we highlighted in yellow. We're saying that's not happening. Additionally, if you're trying to tell me it doesn't happen, that it's not allowed, you have to give me an example. So we say after that, for example, f of 3 is equal to 2, and also f of 6 is equal to 2. That's the one output that was not mapped from a unique input because it had 2 options when we did inverse f inverse of 2. Does that kind of make sense? So you're going to see that question a lot. This is a probable question on an FRQ, is being able to tell me yes or no something is invertible and why. Can we try another one with a different sort of a piece of information for you? Correct. You have no choice. We're doing it anyways. Example 2, same sort of question. This time instead of a table, I gave you a graph. No big deal. We can handle it. We did this last time with function composition. If I ask you f of negative 1, 2. So we go to negative 1. What is the output? 2. How about f of 3?
3. Oh, wait. No. 2.
2. So we go to the input of 3 and we look for the output, which is 2. Okay, how about backwards? F inverse of 3. 4. This time we go to an output of 3.
4.
And we look at the input being 4. How did I get the first one? Negative 1 on the x value. And then 2, and then 3. And then 2. And then for f inverse of 3, I look at 3 on the outputs. The input value that got me there was 4. What about f inverse of negative 1? Negative 2. Very good. Now, the graph shows a relation only or a function. This is looking at the actual one there. Do any of the x values repeat?
Yes.
The x values do?
They do not.
Remember, my friends, this is the time in Algebra 1 where you would have done that vertical line test. So let me take this vertical line, right?
Oh.
And drag it across the screen. Did it, hello, can it drag? Does it cross any of the lines more than once? No. So it's actually okay. Can I get this to go away? That means that this is a function because, again, by definition of this class, we don't just say none of the x's repeat or that it passes the vertical line test. We actually have to say all input values are unique. We're using a more advanced definition to talk about something I know you know from Algebra 1. Let's talk about invertibility. Did we have any repeating output values? We did. So is this graph invertible?
No.
No. This graph is not invertible because, and then we give the definition, all output values are not mapped from a unique input value. And since it's a not answer, since we're saying it is not true, we give an example. For example, And what example can we give here?
F of negative 1
f of -1, what's the output there?
equals 2.
And f of
3
equals 2. Nice. I agree. We could also, if we had more information, any of these things right here, they all repeat in this area. So we could have picked this coordinate point. We just don't know the x value, so I wouldn't pick it. And this one, or any of those where they would repeat. But we have to pick ones we know for sure. So we knew those for sure. Now part E down there says to sketch the inverse relation on the same coordinate plane. Interesting. How can we do that? 2 ways. Number 1, and the easiest way to do this is inverse relations, switch the x and y. So what is the coordinate point of this dot right here?
negative 1,
Negative 2, comma, negative 1. But if we reverse those, and we go to negative 1, comma, negative 2, that's the inverse coordinate point. We switch the x's and y's. What's this coordinate point right here?
negative 1, 2.
So if we switch it, where will we plot the point?
2, negative 1.
To -1. What is this coordinate point? And so if we switch it,
1, 2.
what's this coordinate point?
4, 3.
So if we switch it,
3, 4.
so for each of these, we have switched the inputs and outputs, and we have created the inverse relations graph. And just so that you can see I'm not lying to you, look at the line that goes diagonally across your screen. I meant to make that orange. Hold on. Hello, can you change to orange? There it goes. If we look at that diagonal line, y equal 2x, do you see how it is going diagonally, but also it reflects that line across it? So visually we can see that they are inverses because we switched all the x's and y's, and it's a flip over that line, y equal to x. Questions, comments, concerns? We're feeling okay about coordinate points being inverses of each other. Great, but that's not the only thing that we can do inverses with. We can also find inverse equations. But just like with those coordinate points and we switch the x's and y's, that's all we're going to have to do to find an inverse equation. We will switch the x and y values, solve the equation for y, and then write it as an inverse equation. So for example, we have f of x equal to 3x minus 7. I'm going to switch the inputs and the outputs, which means the f of x becomes an x and the regular x becomes a y. I have switched the inputs and the outputs. With your pencil, I don't even want you to highlight it. I just want you to bold with your pencil. I want you to bold the y. We are going to try to get the y back to being by itself. Because right now, it's on a side with a whole bunch of stuff, and it should be by itself. So what should I do on both sides to start solving for y? Add 7. So we're going to do x plus 7 equal to 3y. And again, bold that y for yourself, because that's what we're trying to get by itself. I have one more step before I'm done. Divide by 3 on both sides. And that means every single thing gets divided by 3. And once we're there, the y is by itself. You're done. All you do after that is make it fancy. The inverse of f is equal to x over 3 plus 7 over 3. I just took the y equals and I changed it back into function notation, notating that it is the inverse of f, so that I've related this function to this function. Switch the x's and y's and solve. Can we handle that? And for 99% of questions, it's like 3 steps and you're done, just like this.
Where's that negative 1 come from?
Well, this is the notation for f inverse. It's not an exponent. That's actually a great question. This is not an exponent of -1. It's the notation f inverse. It's kind of like, remember that time we had hat, like y hat? No, okay. It's just a way that you notate f inverse for the inverse function. Okay, 99% of problems where you're doing the inverse, it's 2 to 3 steps and you're done. If, unfortunately, you're asked to find the inverse of a rational function, there's a significant number of steps involved. So I've done one for you that I want you to annotate along with me so that we can copy and paste those steps and apply it to other problems. So if we look from the question where it started to what's blue on my screen, what did I do from this step to this step?
You flipped the X on way.
Yes, I'm going to use the word switch. I switched the X and Y. Everywhere there was an X, I put a Y. And everywhere there was an output, f of X, I put X. How did I go from that first blue step to the second blue step?
Y minus 2. You sep. Oh, wait.
It looks like I like this went from being over here to being over here. How's that possible? Correct. I multiply by the denominator. Multiply by the denominator. Okay. If we're trying to discover the next step, what happened next? I distributed the X. Nice. So X times Y is XY, and X times 3 is 3X. If you wanted to draw your little arrows right here, might be a good call. And here's the part that always gets people. What happened next? No.
You would add 2. Wait,
Don't you basically just,
would you not add 2 so it's negative?
you divided by, you multiply it by negative something, negative 1.
So it went from being xy plus 3x to the 3x being on the other side. And it went from y minus 2 to having negative y on the other side. So what happened? I moved the 3x to the right side, and I moved the y to the left side. Why do you think I did that? Very nice. I want all of the y's on the left side, and I want everything else on the right side. So I used inverse operations, adding and subtracting, to move all of the y terms to the left side and everything else to the right side. Because like Keela said, we wanted to get the like terms on the same side. And now that they are on the same side, what do these two terms have in common?
They both have a Y.
They both have a y. So I can factor out the GCF of y by dividing each term by y. It's like reverse distribution. And remember, our goal was to get y by itself. So after I have this y out here in front, how did I get it to be by itself? I divided by everything in that parentheses. Once the y is by itself, all you have to do is make it fancy and use the inverse notation. In this exact problem as well, I did actually factor out the GCF of -1, but that's an extra step. Couldn't help myself. Random bonus question, because it's been a minute since we talked about rational functions. What's the number I'm not allowed to plug into this function? Because it would break the denominator. 1. So we'd say x is not allowed to be equal to 1. It's just a good idea to remember if we were doing this problem. Y'all ready to try one together? We have the steps written down. We know exactly what our goal is. We're going to find the inverse of this rational function, g of x equal to 2x plus 1 over x minus 3. What's the first thing I should do? Nice. So g of x, which is an output, becomes x because that's an input. And then it's 2y plus 1 over x minus 3. I mean what? Y minus 3. There we go, not switching the letters. We got to get the y's out of the denominator. So I multiply y minus 3 onto both sides. It will cancel out the denominator of the left side. So it's like I get to take it from the denominator and go plop it into the numerator on the other side. What do I do next? Distribute. X times y is xy, and x times negative 3 is negative 3x. Here comes the step that got everybody before. I'm trying to organize all of the y's to the left and everything else to the right. So if I move this y term to the left, it will become negative. And if I move this x term to the everything else side, it will become positive. So we should have xy minus 2y equal to 3x plus 1. I just move this over here and I move this over here. Now that all the y terms are on the same side, what do they have in common? Y, we're going to factor it out. The things that are left over after I take the y away is an x and a negative 2. We are one step from getting the y by itself. What is it? Divide. If we let that y be by itself, we've divided both sides by x minus 2. Last thing is you make it fancy. F inverse of x is equal to 3x plus 1 over x minus 2. If there was a bonus question on here that said, what number are you not allowed to plug into that? What number is it? 2. 2 would make that denominator equal to 0, so 2 is not allowed. X is not allowed to be 2. I'm going to ask you to do these kinds of problems later, so if you had an additional question, I would rather take it then than right now, because then maybe you'll have answered your own question when you try it on your own. I know you have questions, I'll take them later. Since we are switching the inputs and the outputs of all of these functions, whether it's the coordinate points or the equation itself, to create an inverse function, we must also switch the domain and range of the inverse function. So whatever was the domain is now the range, whatever was the range is now the domain. And I'm saying this, and it's important because sometimes we must use a restricted domain to ensure that the two functions are actually inverses. So if we look at example 6, it says, find the inverse of f when f of x equals to x squared plus 2 for x greater than or equal to 0. What kind of function is this? Quadratic. A quadratic normally looks like this, am I right? Does that have a unique input for every output value? No. There's the same output value here that would happen here at whatever x value this is, and here whatever x value that is. So to actually find the inverse here, we're going to have to chop this equation in half. And in fact, that's what it's telling me to do. Here's where x is equal to 0. And what it wants me to do is it wants me to straight up get rid of one side of the parabola. So we have to have restricted our domain before we even started this question so that we can actually find an inverse function. But let's say we didn't even read that part of the question because we're going fast and we're not reading our questions exactly right. So we have f of x equal to x squared plus 2. If we're finding the inverse, what is that first step from the top of this page? What does it tell me to do? So that means this will now be x equal to y squared plus 2. Let me solve for y. How do I start to solve for y? Remember, it's this y right here if we're bolding it with our pencil. X minus 2 equals y squared. Very nice. Now again, I still want just y by itself, so I got to get rid of that square. Square root. Now when you take the square root of something, what do you have to put in front of that equation? A plus or minus. So this is plus or minus the square root of x minus 2 equal to y. Here's why we had to stop for a second before this problem started and actually read this part right here. since it wants only half of the parabola, because we say that x has to be greater than or equal to 0, it wants only half of this answer. So we have to decide if we're wanting the plus version or the minus version. So my question for you, and don't overthink it, if we're having x greater than or equal to 0, are we wanting the part that's above the x-axis or below? Above. So in this problem, we actually just want the plus side of this. So our inverse equation, f inverse of x, would just be the positive version, x minus 2. If it had said that x has to be less than or equal to 0, we would have wanted the negative version of the plus minus. And here's why this makes sense. Because if we look at the parabola that was chopped in half, we would say that the domain of this parabola is only from 0 to infinity instead of all real numbers. Yes?
Is that supposed to be a plus in the final answer?
You don't have to actually put the plus. That's a great question. You have to put the minus if it's minus. You don't have to put the plus if it's plus. Kind of like with numbers. 5 is positive 5. Great question. And since this is a restricted domain, we had to take our range that from this question was negative infinity to infinity and also restrict it, to 0 to infinity. So a restricted domain causes a restricted range in its inverse. A restricted domain causes a restricted range in its inverse. Now, finding these inverse functions, it is a little bit challenging, and that's what we're going to practice outside of notes. But on your last page of your notes, I'm going to introduce to you how the first FRQ might look. The first FRQ, or all of the FRQs in this class, are very laid out for you. They're going to be the same types of questions over and over again. Okay? In FRQ number 1, you will be given either a table or a graph, as well as, eventually, because not today, as well as a second equation. And your job is to answer questions about either the table, graph, or the equation. Here's the kind of questions that you might be asked. It says in part A, find the value of f inverse of -1 or indicate that it is not defined. Well, you guys answered this question earlier. What is f inverse of -1 for this table?
4.
So here's how you answer this entire FRQ and get a whole point. F inverse of -1 equals 4. The end. You got a point. You can get that point, can't you? Another question that might be asked on FRQ1 will look like this. It might say, determine if an inverse function of f can be constructed for all values in the domain of f. So we're looking here. It's a yes or no question. Can you make an inverse function out of these inputs and outputs?
Yes.
Ooh, I hear yeses and I hear nos.
Oh.
Yeah.
Remember, to make an inverse, we have to look at the outputs and make sure that all of those are unique. To look at it and ask if it's a function is looking at the x's. To ask if its inverse is a function, it's looking at the outputs. So because we notice this, we're going to say no. An inverse cannot be constructed. How did I know to use those words? I read the question. It says, determine if it can be constructed. So I say, no, it cannot be constructed. We're just returning the question back to the reader. Then part 2 is always going to ask you to give a reason for what you said. And Keela already said it out loud. Keela, why can this one not work? The 4s are going to repeat on the outputs, but we have to make sure we're using AP Pre-Cal language for this. So we're going to use that highlighted sentence from the beginning of our notes. And if you have to look back now, that's fine. We're going to get used to writing it. We would say they're not unique. So we say all output values are not mapped from a unique input value. For example, f of 2 equal to 4, and f of 5 equal to 4. And this is why I introduced that language of how we're speaking it early in these notes and early in this class, is because I know that this is how it was be asked on one of the FRQs.
So if you don't say the answer this way, like, but you say it another way, it would count, but you don't, I mean,
It would not count unless it's using the definition of a function. And in this class, based on the CED of this class, the definition of a function is that you have unique input values for every output value for an inverse function. Now you can say extra stuff. You could also say, this also means that it does not pass the horizontal line test. That's fine, but you have to talk about the definition from this class.
basically just look at the answer and take the words from the, I mean, look for the question and take the words from the question and write.
Basically, yes, because you have to show that you understand the level that this class gets to, not just the no repeating x's and no repeating y's from Algebra 1. Let's try it again. Okay, the figure shows the graph of the decreasing function f on its domain for all real numbers where x is not equal to 1. The points 0, comma, negative 1, comma 0, and 3, comma 2 are on the graph. And since it gave you this, when I did this question, I went ahead and made those dots pretty obvious for myself, just so that I guaranteed myself I understood what it was talking about. Now for part A, number 2, it says find the value of f inverse of 2, or indicate that it is not defined. F inverse of 2. Yeah, remember this is now an output, f inverse of 2. So we go for the output is 2. What's the input? 3. Very nice. So we say f inverse of 2 is equal to 3. The end. That's a point. Now we're going to determine if this function f, the graph, is invertible. So we look at all of the outputs. Do any of those output values repeat? So we can we think about the horizontal line test. Does it pass the horizontal line test? It does. So determine if f is invertible. This is the first time we're going to see it. We're going to say yes, f is invertible. Now I know things that we want to say are that none of the output values repeat, but remember we're using the language from this course and the definition of a function. And since it's a yes question, we don't have to give an example. We just have to be very particular about our wording choice. We would say for this one, for all output values of f, we refer to the function, because we can't give an example, so we refer to the function now. It told me to refer to the function. For all output values of f of x are mapped from unique input values. We don't give an example because we're trying to prove that it is. We only give examples if we have a counterexample to show that it's not. All input values of this function f of x are mapped from unique input values.
Because they don't, there's not two, right?
Correct, because none of the output values repeat, they are all mapped from unique input values. Because it passes the horizontal line test, all of the output values are mapped from unique input values. So I know we understand the concept of no repeating y's, we just have to get the language down correct.